Hi guys, this is Miss Scott. In this video, we are going to talk about, and this should actually say section 4.7. We're going to talk about using isosceles and equilateral triangles. So it's actually split into two parts. The first we're going to say what is true about the base angles in an isosceles triangle, and then what's true about a triangle's sides if it's equiangular. Well, first we need to define a few things. We got to talk about the different parts of an isosceles triangle. The first part is the leg or the legs. Those are the two that are congruent. So like this would be one leg, this would be another leg. The second part we'll talk about is called the base, which is where the two congruent parts meet. So that would be right here. All right, so it's the non-congruent side. All right, and then there's names for the angles as well. The base angles would be the two angles that are congruent. So for example, this angle here and this angle here. And lastly, the vertex angle is the one that is not congruent to the other two. So we've got a couple theorems about equilateral and equiangular triangles. The first is the base angles theorem. And that one just tells you if two sides of a triangle are congruent, so we're just going to draw a little congruent symbol there, then the angles opposite them are congruent. All right, so in addition to that, there's a corollary, which means like in addition, if a triangle is equilateral, then it is equiangular. All right, so if you know you have an equilateral triangle, it turns out all of the angles are the same as well. All right, and the converse of that says if two angles of a triangle are congruent, then the sides opposite them are also congruent. And in addition to that, if a triangle is equiangular, well, then it is also equilateral. So we know all three sides would be the same if all three angles are the same. Okay, so let's take a look at some examples with this stuff. All right, so we're going to use this picture of triangle IRT to answer questions 1 through 4. The first one is asking us what kind of triangle is triangle IRT? Well, I've got two congruent sides, so we know that this would be an isosceles triangle. And the base angles are the two that are across from the congruent sides. So that would be angles R and I. All right. The vertex angle would be the one where the two congruent sides meet, so that would be angle T. And we can use some algebra here to find the missing angle, angle T. We actually know that R has to be the same number of degrees as I because those are the base angles and they're congruent. So we know those are both 58 degrees. And I'll call this up here X. Well, we know X plus 58 plus 58 has to equal 180. If you add those together, you end up with X plus 116 equals 180. So if you subtract that 116, you would get your X of 64 degrees. All right, let's look at another example. So in the next one, we have all three angles here are the same. So if it's equiangular, it's also equilateral. So I'm going to say this is an equilateral triangle. And then how long is AB? Well, if it's equilateral, these are all 11. So AB would be 11 units long, CA would be 11 units long. And then the last thing is, what are the angle measures in an equilateral triangle? Well, you've got 180 degrees, and if you split it up evenly 3 ways, each of those angles is going to be 60 degrees. So angle A is 60 degrees, angle B is 60 degrees, and angle C is 60 degrees. So all three angles are 60, and you'll notice that those add up to 180. All right, let's move on to a couple of examples using some algebra here. So in example 1, we have, notice that all three sides are 10 units long, so this is going to have to be equilateral. Well, if it's equilateral, we know this angle and this angle and this angle are all the same. We just talked about that. They've got to be 60 degrees. So to find x, all you have to do is say 5x equals 60, divide both sides by 5, and you end up with x equals 12. Okay, let's look at an example that's a little bit tougher, but we can still do it. All right, so notice that we have an isosceles triangle. They tell us that angle E up here is 40 degrees, so we can actually figure out what these two are because we've got 180 degrees all together. If we take away that 40 degrees for angle E, we're left with 140 degrees, and we have to split that between angle D and angle F because those have to be equal. And that means each of those is going to be 70 degrees. So our equation to set up is 11x minus 18 equals 70. This angle here has to be 70 degrees. Okay, so if we go ahead and add the 18 to the other side, we end up with 11x equals 88. And if you divide that by 11, you'll get x equals 8. Okay, so that was a little trickier, but not too bad. We still got it. Okay, so let's look at number 3. In this one, they give us an expression with x in all three sides. So if this is equiangular, we know all three sides are the same. So really, guys, just pick 2 that you want to set equal to each other. I'll use 7x plus 2 and 2x plus 17, but you could have used the other one. I'm just going to go with these. I'm going to say 7x plus 2, that side, has to equal the 2x plus 17 side. So let's start by getting our x's all on one side. We end up with 5x plus 2 is equal to 17. Subtract 2, you get 5x equals 15. And if you divide by 5, 15 divided by 5 gives us 3 for our x value. Okay, now examples 4 and that last one, that proof, are going to be a little bit more time consuming. So hang in there, guys. In example 4, we've got to use quite a bit here. The first thing that I notice is, let's see, how can we start this one? Well, if you look on the far right-hand side in this triangle over here, this is an equiangular triangle. So if it's equiangular, we know that all three of these sides have to be the same because equiangular triangles are also equilateral. So this has to be 12 right here, and then this has to be 12 right here. And then this is an isosceles triangle, so we've got 12 over here as well. Let's see, how can we go from here? Now we're going to use some angles here as well. Remember, equiangular triangles, all of these are 60 degrees. And we've got right here a 90-degree angle. Okay, so I think where we should start is by finding the value of x. If this triangle in the middle is isosceles, we know that angle S right here has to be x, and so does angle T. Remember, those base angles are congruent. So we can find this angle measure right here. So that angle measure, see, we've got this linear pair right here. So if we take 180 minus 90 minus 60, that's going to leave, let's see, 180 minus 90 is 90. 90 minus 60 is 30 degrees. So that angle in there is 30 degrees. And now we can set up an equation to find x. I've got 30 degrees here. I've got an x plus an x. Those three have to make 180 degrees. All right, I'm going to move this over a little bit so we've got some room to work. So 30 plus 2x equals 180. Go ahead and subtract your 30 from both sides. These cancel. You get 2x equals 150. So if we divide by 2, x is 75. All right, now we just have to find y. Now, we're going to kind of work a little bit ahead of ourselves. I haven't taught you guys this theorem yet, but I'm going to call this right here from R to V, I'm going to call that A. And if you recall, we have this theorem that says a squared plus b squared equals c squared, and that works for right triangles. Well, since this triangle on the left-hand side is a right triangle, we can fill in for b, that's the 12 on the side there, and that equals the hypotenuse squared, which is 15. All right, so 12 squared is 144. 15 squared is 225, so we're up to a squared plus 144 equals 125. Go ahead and subtract your 144 from both sides. These cancel. We end up with a squared equals 225 minus 144 is 81. And to get that square out of there, we can square root and end up with a equals 9. All right, so last but not least, if we know this from here to here is 9, and from here to here is 12, y is just going to be 9 plus 12, which is 21 units. All right, that was a tough one. Okay, let's do one last example. We're going to complete this proof here. We are given that this segment DB bisects angle ADC. So let's write that down. BD bisects angle ADC. That's our given. So now we actually know angle 1 is congruent to angle 2. That's actually just the definition of a bisector. So we know if an angle bisector, it cuts it into two congruent angles, so that's why angle 1 and angle 2 are congruent. All right, we're going to switch gears a little bit here. We also know that DB is perpendicular to AC. That was another of our givens right here. So that is given also. And if we know that's perpendicular, we know that angle 4, oops, writing in the wrong spot, angle 4 has to be congruent to angle 3 because if these are perpendicular, we know all right angles are congruent. All right, now why do we know that DB is congruent to itself? Well, that's just the reflexive property. All right, now look at your triangles. We've got an angle, a side, and an angle. And over here we have that same angle, side, and angle. So ASA tells us that the two triangles are congruent. So the triangle on the left, or the triangle on the right, triangle ABD, is congruent to triangle CBD. All right, and then we can say all the corresponding parts are congruent. So in this case, angle C is congruent to angle A by CPCTC. And if you know that the base angles are congruent, that has to be an isosceles triangle. So we got to what we're trying to prove here. It's because the base angles are congruent. and that makes it isosceles. Whew. All right, guys. Thank you for watching. If you have questions, feel free to comment down below. Like the video, subscribe to my channel, and we will see you guys next time.